chapter 3.6 today. What we are going to be basically doing is taking a lot of the concepts that we have been talking about in 3.1 through 3.5 and interpreting those values from a regression output from a computer. So here it says interpreting computer regression outputs. Our calculator does a lot of this stuff for us. Okay? But there's also a lot of different statistical software programs out there that can analyze large sums of data. I don't know about you, but I would not want to try to do a scatter plot on 500 pieces of data on my handheld calculator. I'd much rather, have some way of entering in a database of some kind into some computer software. The nice part about it is we don't actually ask you to input all those values, but to be able to take some sort of computer software's output and be able to identify some of the key pieces from them and interpret the information in the context of how the problem is set up. So, what you need to be able to identify quickly, as it says in this little paragraph here, you will need to identify the slope, the y-intercept, the values for the standard deviation of the residuals s, and your coefficient of determination r squared. From those values, you can actually determine even more pieces of information. But if you can identify those four key pieces and know how to interpret them in the context of the problem, a lot easier that this will be. Now on this front page, we give you two types of computer outputs that you might see in your homework. Okay? The one on the left is from a program called Minitab, and the other one is from a program called JMP. Both of them, again, are good statistical software programs. Now, how you identify these values are actually circled up here, but I just want to kind of know where I start to look for them. A lot of the programs are going to give you this large set of data here. You can see it even on here where it says parameter estimates, and you'll have either something that says estimate or coefficient, standard error, TP. All of these values for our course right now will not have any significant meaning. Later on, we might get to using some of those values, or we'll at least show you how some of those values come to play. But the biggest values that we first want to find is, this is an output basically on regression. Regression equations is something that basically an equation that best fits our data. The one we're exploring the most in this class is the linear equation. So we need to find out what is slope and y-intercept. So some of the programs will actually say intercept, or they'll say the word constant. Constant means there's no variable involved. So in the equation, if you think about your prediction equation, y equals a plus bx, the constant is the a value, the y-intercept. So you'll either use the word intercept, so that's why it says y-intercept here, or here it says constant, which is another term for y-intercept. Coefficient represents the number in front. Well, since there's no variable with a constant, it's actually just that particular number. So our y-intercept in both cases would be this 3.505 ... Now, the number in front of the x value is our slope. Now notice how both of these have this word NEA change. That's what the x variable is. So many times what it will do is it will give you what the x variable represents in the table. So the coefficient or number in front of the x is your slope. Notice here this will also be slope. So we have our y-intercept, we have our slope, then we could write our equation. So if I wanted to write this particular equation, it might look something like this. Y hat equals 3.5051 minus 0.00, I'm so close, that is it 3.441 for 1x. So notice how the slope here was actually negative. So I have my equation. So now, we have slope y-intercept, we got our least squared regression equation. So we have our prediction equation. So now we have to identify the standard deviation of the residuals, otherwise known as our average prediction error. So what's nice about this is they use S for us in both programs. You'll see up here, they actually like to use the term root mean square error. So if you see that terminology, it's the same as the standard deviation of the residuals. But for the most part, most programs will kick it out as S, our standard deviation of our residuals. So that's the, again, average prediction error. Then we look for R squared. Now if you look on both programs, they actually have an R squared and an R squared adjusted. I really wish they didn't do the R squared adjusted on there because sometimes it confuses students. So right away, I cross out R squared adjusted because we're not adjusting our R squared, we just want the straight up R squared value. So for instance here, my R squared, I am told as 0.6061. Well, if I have the R squared, could I find R?
Yeah.
What would I do to both sides? Square root, square root. What goes in front of the square root? Technically, plus or minus, because R could be positive or negative, couldn't it be? So just out of curiosity, let's see here, what's the square root of 0.6061? So if I go square root, 0.6061, I get 0.7785. And the question becomes, is it positive or is it negative? How would I be able to tell by the information from the program whether this R value, this correlation coefficient, is a negative relationship or a positive relationship? If I were to graph this equation, would my line be going up or would my line be going down?
Down.
Why down?
Slope is negative.
Slope is negative. So what should be true about the correlation coefficient?
Negative.
It should also be negative. So R has the same sign when I'm talking about same sign, positive or negative, as the slope. So again, when you're trying to find correlation coefficient, you do just simply take the square root of R squared, but you got to remember, is it positive or negative? So this tells us that we probably have a moderately strong negative linear association between NEA change and whatever the Y value is. They didn't really give you a context here. We know what X is at least. All right. Are you guys ready to see one of these in actual action?
Yeah.
Woohoo! Love the excitement. All right, next page. Here's our example problem. Wow, does it have a lot of information.
Very.
So it says, how well does the number of beers a person drinks predict his or her blood alcohol content, or otherwise known as BAC, blood alcohol content. 16 volunteers with initial blood alcohol content of 0 drank a randomly assigned number of cans of beer. 30 minutes later, a police officer measured their blood alcohol content level. Least squared regression was performed on the data. A scatter plot with the regression line was added, a residual plot, and some computer output from the regression are shown below. Wow, you have just a ton of information given to you. Already done. They did the scatter plot for us. Here's our scatter plot. Here's the line of best fit. So they already put that in there for us. They did the residual plot for us. And they give us the output, giving us all the different variables that we just have to identify. So I am going to shrink this a little bit here so I can see and still do some of the problems at the same time. So in question A, says, what is the equation of the least squared regression that describes the relationship between beers consumed and blood alcohol content? Define your variables. Probably the most important thing to do at the beginning. Let's define x and y hat. So if you were to define x, what does x represent? Number of cans of beers. So, number of, I suppose we could just say beers consumed. Then y hat is going to be what? Okay. Okay. It's the predicted blood alcohol content, BAC. I'm just going to write blood I'm sorry. I think I misspelled alcohol. H-A-C-O. I might just do a little erasing.
I didn't go this year. Next year's the last year. I just got it. It's well, they're relocating it.
All right, so now that I have my variables defined, I still want to find my equation. Again, y hat equals a plus bx. So what number up here is going to represent my y-intercept? What word would I look for in my variable for y-intercept? A coefficient and what? So it's going to be one of these two. Is it the constant or the beers? It's the constant. There's no variable in front of it, so that's the y-intercept. So knowing that it's several decimal places, I'm going to round it probably to just 3 here. So I'm going to say y hat equals negative 0.01, I'll go even out 4, 127. Sorry, what was the question?
Why did you choose the constant?
Because that's the y-intercept. Because there's no variable for a y-intercept. Is there a x or a y with the a? No. So when I go up here, constant beers. What does beers represent? X. What's the number in front of the x according to my equation? Slope. So this number is our slope.
Why are all the other numbers?
Well, as I explained on the last page, we cross these numbers out. So now our slope plus 0.01796, I could round that to 80x. So now, I have my equation. Part B says, interpret the slope of the regression line in context. So what does this 0.0180 actually represent? So that's my slope. What's positive? Yep. So what's going up? Okay, so the predicted blood alcohol content increases by 0.018, I suppose you could say percent, for each additional beer or one beer consumed. So question C now asks for you to find the correlation coefficient and interpret the coefficient of determination in context. Correlation coefficient is what variable? That's R. Coefficient of determination is
Squared.
R squared. So our R squared value, according to our table, 0.80. Again, adjusted, we ignore. So, remember, this is that fill in the blank sentence that we talked about yesterday. So we would say blank percent. So in our case, 80% of the variation in the y values. Well, my y values would be in the predicted blood alcohol content levels can be accounted for by the least squared regression equation. So 80% of the data, or 80% of the variation in my predicted y values are accounted for. So it's getting 4 out of 5 of those predicted values. Pretty solid. We'd like it to be even better, but still pretty decent. Or still need to find R squared. Or sorry, not R squared, but R. So what do I have to do to this? Square root. So, on my calculator, square root. Oops, sorry. Gotta make sure I'm doing the square root of 0.8. 0.8944. Is this R positive or negative? You can tell it's positive a couple ways. Positive slope, the line is positive. So I know my R is a positive 0.8944. So what does that tell us? We have a very, you know what, I might even increase this so it's a little bit easier to see. So we have a very strong, positive, linear relationship between the number beers consumed and the predicted blood alcohol content level. So now in part D, it asks, is the line an appropriate model to use for this data? Well, does it seem like our line fits our data pretty well?
Yeah.
Okay, what else other than the scatter plot in the line of best fit help us determine this? Okay, what about the residual graph here that I haven't even talked about yet? It's all over the place, no pattern. So if our residual graph gives us no pattern, then that tells us our least squared regression line or equation is the best fit. So is this an appropriate model? Yes. Our residual plot is scattered with no obvious pattern which tells us our least squared regression line is a good fit. So now, in E, our last one here, says, what is the blood alcohol content reading for the person who consumed 9 beers? Show your work. Okay. Well, if we first look at the scatter plot, let's estimate it. So if I go up to my scatter plot, where does this look like it's around? 9 beers. Okay. So if we read our scale here, this is 0.15, this is 0.20. So maybe somewhere between 0.17, 0.18, 0.19. It's kind of somewhere in that range. So somewhere between 0.17 and 0.19. But can we get a better result? Okay. Could we find out what the predicted value is? Okay, so how can I actually find this predicted value? Yeah, let's plug it into our equation. So I'm going to go to the y hat equals, and what I'm doing right now is I'm just grabbing this equation, this negative 0.0127 plus 0.018, and I'm timesing it by 9 because the person consumed 9 beers. So, negative 0.0127 plus 0.018 times 9. So right now my predicted value is 0.1493. But what value do I actually want? I want the observed y. I have the predicted y. So what formula do we have that relates observed y and predicted y to each other? What's this formula called? No, not y-intercept. Y minus y hat. Hey, there we go. Residual. So, can I look somewhere and find the residual value for 9 cans of beer? Where?
In your calculator. Somewhere you hit.
Well, do we have this stuff in our calculator?
No.
Okay, but somewhere in the stuff they gave us, do we know what the residual value is for 9 beers? Where might that be located? On which graph?
The
Residual graph for 9 beers is right here. What is that residual value? Yeah, it looks like it's right at 0.04. Okay? So, we go back down to here. My residual from my graph was 0.04. I want y. I have y hat. Could I now solve this basic algebraic equation for y?
Yeah.
So let's add 0.1493. So y is 0.1893. So we could say the blood alcohol content of a person consuming 9 beers is about 0.1893%. Is that over the legal limit?
Yeah.
Yeah.
That's a lot over.
Well, if you're driving or you're in public, yeah, 0.08 is the legal limit for at least driving or being out in the public. So we're talking like almost 2.5 times above what they defined as the legal limit. All right.